Thank you all for having me here today. My name is Tristan Eggenberger. I'm representing Team 6, Sandia High School. And our project is SINGS, a simple interactive n-body gravitation simulator. We're going to unpack what all those scary words mean in just a bit. The big one, though, for the purpose of this presentation, what is an n-body simulation? So the crux of this is n-body simulations. An n-body simulation, for my purposes, is a simulation of the gravitational interaction between n different bodies or n different objects. So, this means generating different objects, different particles on a computer. We can represent certain astrophysical systems, like, planets going around the sun, star systems forming, stars going around the center of the galaxy, and galaxies themselves colliding to form the large-scale structure of the universe. Here you can see different snippets from major simulations at NASA and other major institutions across the world have done that. It really changed our perspective about the history of the universe. Briefly, I'll just go into the history of these, not too deep though, just kind of lay some groundwork. So the first instance of n-body computation for making astrophysical predictions, which is what these things are so useful for, was by the French astronomer Urbain Le Verrier, who was able to use the deviations in the orbit of Uranus to predict the existence of Neptune. And they were able to find it on the same night that his letter arrived at the Berlin Observatory. And about 100 years later, via Swedish astronomer, 40 years before the advent of modern computing, who was able to understand the dynamics of colliding galaxies and how they spread apart under their mutual interaction, using a ingenious setup using light bulbs and things like that. It's really brilliant. And now today, as computers have gotten more powerful, we can simulate these complex systems with remarkable accuracy. In the top right there, you see the Illustrious Project. It's one of the biggest simulations out there. There are trillions of particles here that can represent individual galaxies to incredible resolution, and then seeing how they interact with each other, it gives us a good understanding of, the history of the early universe. We can only see the universe through these instants in time. These simulations give us a tool for understanding the wider universe. So what is SINGS? SINGS is, as I said earlier, it's a simple interactive n-body gravitation simulator. It's a tool for which these complex astrophysical simulations can be generated, ran, and diagnosed. The primary tool, or the primary goal, is it being a tool where one can, with ease, translate an astrophysical system to what's called a SING snapshot. So right here, this is an image of the bullet cluster. It's two galaxy clusters that are colliding with each other very quickly. And the goal with SINGS is to have a tool where someone who's interested in studying the behavior of these systems could very easily put in the starting conditions, how fast each of these galaxies are moving, and let it fly. And this is huge for understanding bits of cosmology, because it's through the bullet cluster that we get a lot of our understanding and evidence for things like the existence of dark matter and dark energy. So how does SINGS work? SINGS works through a very simple 5-step process. We initialize the simulation. This is a lot more complicated than it sounds, but SINGS allows users to create these setups and then load them into the simulation software itself. And then after that, we compute the forces on each of the objects in our simulation. And then through that, we do what's called particle integration. We update the positions of these objects. We apply these forces. And then a new bit of SINGS that has been added in the last few months is particle collision resolution. So, not all matter passes through each other. Dark matter does, but particles of gas can collide, and that's modeled through simple kinematics. And then after that, we dump the simulation state. So the user can specify how often they want to, release what the simulation looks like at an instant in time. They can create a bitmap visualization of it. It creates a little image of it. They can use these to create, animations of the evolutions of these simulations, and I can show a bit of that at the end here. But it's through this very simple loop that the entire program runs, and because each of these different phases of program execution are completely independent from each other, it makes things incredibly modular, because you can I can simply just add in another force calculation algorithm, and it's not going to mess with any other part of the system. And that's what makes it so easy to develop. It makes it so easy to get useful results from this. So integrators, we're not going to go into all these formulas, but these are the different ways by which the simulation is updated. There's a lot of theory behind which ones are good, which ones are bad. But these are just kind of the most common methods. There's the Euler methods, there's Runge-Kutta, and then there's a method of integration called leapfrog integration, where all these vectors, R represents position, V represents velocity, and A represents acceleration. And then delta T is the time step of the simulation itself. But that's not the main part of this. The main big part of this is force codes. There are two primary force codes in SINGs that have been extensively validated and made parallelizable. There's the direct method. This is the most simple way of computing forces between bodies. What you do, you have a particle, you compute the forces between every other particle, and this will produce exactly the force acting on that particle at a given time. Problem with that, though, is it scales with O of n squared, which means if you have 1,000 particles, you have to do a million different computations just to compute forces on each of these particles. But there is, an alternative method that we provide. It's called Barnes-Hut method. And how it works, and we'll see this on the next slide, is it drastically reduces the number of computations that we need to do because it divides the space. In this case, this is a two-dimensional visualization, but it divides the space in 2D quadrants in 3D octants. And it constructs this tree where what you can do is just say for an individual particle over here, it can approximate all the particles over here as just one big particle instead of having to do 3 different computations. And so on the next slide, we'll see kind of a more insane version of that. Barnes had elaborated, it's inherently an approximation. How it works is we evaluate this ratio. L over R is less than theta. Theta is some tunable parameter. You can set it to whatever you want, and it will determine the accuracy of your simulation. L represents the side length of each of these different boxes right here. And R is the distance to the center of these boxes. This isn't exactly how it's represented internally, but this is the general theory behind it. And for different values of theta, you'll get different errors, and it tends to grow exponentially, as you can see in this graph. But what's interesting over here, we have a two-dimensional simulation of two galaxies colliding. This is showing the different Barnes-Hut approximations that are being used to calculate the force on this particle. Now, in this simulation, there are over 12,000 particles, but there's a countable number of boxes here. It's representing this entire part of this galaxy as just a single object, and that drastically cuts down on the computations and drastically speeds up simulation performance. And so for large-scale simulations, this is the method that SINGs will generally employ, but both can be used. In fact, we'll often use the direct method as a benchmark because the direct method will always give an exact result. Even though it's slow, you can use it to test the accuracy of different simulations. So now on to parallelization. This is a big thing. There's not a lot on this slide, but there is a lot to talk about. SINGs benefits a lot from being able to use multiple CPU cores. And we do this through the use of OpenMP. It's this open source library for the C programming language and a bunch of other programming languages, I'm sure. But as you can see, for different integrators here, as the number of threads, the number of CPU cores you give to SINGs goes up, the runtime, or more specifically, 1 over the runtime, tends to go up. And that's correlated with a significant reduction in simulation time. So this morning, I just ran like this very simple benchmark. A 1-minute simulation, single thread with 10,000 particles would take a minute to do, at least on my laptop. But with 8 logic cores, it takes nearly 10 seconds. And that's just a single benchmark. There are plenty others, but the specific data points here were gathered on far larger simulations that took many multiple, dozens of minutes and things like that to fully execute. So parallelization is a super important thing because we want this to be able to run fast to compute the simulations quickly. We can validate the simulations through different ways. These are a bunch of graphs that I'm throwing at you. But these are just evaluating the different errors throughout a simulation depending on which tools that you're using. And SINGs provides you this data when you want to run a simulation. That way when, for example, an integrator that you're using might not be ideal for the task. different time steps will result in higher energy loss or energy gain put into the system. So you need to take account of that. We saw this earlier. And then this graph down here describes the softening of forces because we implement a softened gravitational force model. If two particles get too close, if we didn't do that, you'd be dividing by 0 and causing the whole thing to diverge. So just kind of a general conclusion to wrap up here, and kind of the future of this project. At the end of the day, SINGS is an engine. It's an engine for creating large simulations. In the future, we want verbose simulation logs. We want people to know exactly what SINGS is doing at any given point in time. That way, it's much more useful. You can debug errors better. Increasing the number of generation tools in the simulation compiler, like arbitrary eccentricity elliptical galaxies. So you can make galaxies however oblong you want. You can make different types of spiral galaxies, things like that. Tools for making planetary systems. And then more detailed snapshot rendering tools, though they do exist. And I do have some exciting animations to show there. And then lastly, support for periodic boundary conditions. And that's actually kind of ties in to that last point. Periodic boundary conditions, essentially, if you're simulating a large simulation space that's representing the universe, it's only going to be computing the forces within that local block of space. But the problem with that is if you go here, here's a simulation of a couple thousand particles. What happens is everything tends to begin to fall inward. And the problem with that is that's not what the large scale universe looks like. It's not these big homogeneous clumps that have collapsed in on each other. There are bits of space over here that would be interacting with bits of space way outside the simulation space. Periodic boundary conditions allow us to deal with that. All of that being said, there's some sources and references, but I now welcome your questions. There's a lot there. There's a lot here that, I couldn't possibly go into such excruciating detail on. Even in my paper, there were so many things that I wanted to talk about. So I really invite any and all your thoughts and comments on this.
Can you go back to the figure 4 in your report that's showing the quad trees or oct trees?
The
side by side.
Yeah, this one.
The next with the 2 galaxies.
Oh, with the 2 galaxies, yes. I put more.
There you go. Yeah.
I can probably, I have the original files on my computer. I can get them for you right now. It's probably right here.
Yeah.
So this is the original without the red arrow.
So you have a side by side in your report.
Yeah.
Where basically you have that on the left-hand side, it's fully quad treed out.
Yeah, that's every single.
You're saying there's a particle on the left?
Yeah, the particle on the left, it's really hard to see in the report, but it's this little red square that kind of highlights. And I think it's right on the boundary. I think it's this particle right here. The simulation renderer renders from the top left and drawing the particles.
Where's the particle?
The particle is,
right. Okay.
It's this little block that's sticking out. This is from an earlier version of the rendering tool that was primarily made for 2D.
Okay, now if you can zoom out. So my question is,
yes.
So when we look at the right, where it's not, that galaxy is not quad treed up or oct treed up, that is from the perspective of that particle.
Yeah. And
so if there was another particle in that quadrant, it would reuse this quadrant? That's the question. I see.
If there was another particle, what would happen is the rules for generating the quad tree, and same with the oct tree, is that they all use the same quad tree. However, they all use the same quad tree. The quad tree is built every single simulation frame. If there was another particle, say in this same region, this would be divvied up a little bit more because every single one of these bounding boxes, if you look at the original in my paper, which I can find in here somewhere. There you are. If you look at the original, there you are. Every single box, if you look very carefully, will only ever contain one particle. So if there was another, they all use this exact same tree for deriving their stuff, just the limit to where they're cutting off the approximation and going further, that's the thing that's different. So it would likely, if I'm understanding the question correctly, it would likely approximate the galaxy to be roughly the same as the particle.
So it'll go through that same cutoff process.
Likewise, yeah.
Okay.
And the cutoff is the same for all the particles.
Yeah, definitely.
So, just in your report, you mentioned that you started looking at this last spring break.
Mhm.
So I was curious where you were at the beginning of the school year and what you've done since then.
Right. So this project, in its earliest form, I very much remember the original version. I might have it on like a private repo on my GitHub or something like that. The original version was, it was kind of just, we had finished the gravitation unit in AP physics, and I just wanted to see if I could use like this rinky-dink like OpenGL graphics library just to see two planets orbiting each other and maybe throw in a third. It wasn't anything serious until maybe April, May, around that time, when it turned into a 2D project, and that's called Stings 1, which I still have. At the start of the year, what this was it was a very kind of haphazardly thrown together two-dimensional simulation renderer that had a lot of memory leaks. It only had a single integrator, and it did have Barnes HUD implemented, but again, only in the two-dimensional case. So it was using quad trees instead of block trees. It wasn't this modular system. There was a lot of overlap. It was very messy. Throughout the course of this year, the main development has been in breaking up the various parts of SINGs into being their own distinct units. If you recall just this graph right here, back at the start of this whole endeavor at the start of the year, you would have lines constantly, crisscrossing over each other. Whereas now, in essence, how this works, this very, even though it's C, it's not object oriented or anything. How it basically works is all these different components are playing hot potato with the simulation. They're just tossing it back and forth. And because of that, there is no inherent overlap. I made it a point such that anytime I needed to use one function from one thing, I could do it without it ever interfering with other parts of the program itself. And then throughout that, it's been adding in additional integrators. I wanted to add in an additional force calculation. I talked about it a lot in my February evaluation. I was working on the particle mesh method, which is another way of doing this. It involves fast Fourier transforms. But the present implementation, as good as it's gotten, as polished as it is, was not supportive of it. But that is part of the extended roadmap, because the thing that I want to implement is something called smooth particle hydrodynamics. It's a method of computing how gases interact with each other. Right now, gases are just these kind of kinematic molecules that bounce off of each other like billiard balls, which isn't entirely realistic. But throughout this, there's been a lot of error resolution, being able to develop these diagnostic tools, and also increasing the dimension had a big aspect of it, because there is, I highly doubt if there is any code overlap between this version of SINGs and the one from the start of the year, because everything for the most part has had to have been torn out and re-put back in this more condensed format. But the perks of that is that the code readability is far better, because the main simulation loop, for the most part, it's just a for loop, and you have these list of functions. You just pass in the pointers to the functions depending on what integrator you're using or force code, and it all just seamlessly interacts. That's been the main struggle with this, as I've learned to become a better programmer, is going from something that was kind of bodged together with the original version, the two-dimensional version, and bumping it up to 3D. Thanks.
So you said you used OpenMP, and if I remember, OpenMP is shared memory, is that right?
OpenMP is, yeah, it is shared memory. It's not conducive to the node-based architectures of supercomputers.
Well, the thing I just wanted, so basically this code is limited by the amount of memory that you have.
Yes, it is. But what I found kind of surprising is how much accuracy and fidelity you can get out of cutting corners in terms of bytes. I'm a big C and low level programming fan because I like making things as efficient as possible and using as little memory as possible. For example, like a big point that reduced the memory usage by more than half was instead of using doubles, I use floats for most of this stuff because the simulation bounding box is pretty small. And so because of that, you don't need the double, floating point precision to get highly accurate simulation results. And that cuts, the bytes that each particle is taking up. It's 9 vectors that are each, have an X, Y, and Z component, and they're all floats. That's saving a lot of memory. And so the memory usage, I don't think is too big of a problem. The computation is definitely the limiting factor, at least on my computer.
So, I mean, anything you do is going to have limitations.
Yeah,
so,
yeah, absolutely.
So it's important to stay with those limitations are.
Oh yeah, I couldn't agree more. But what I found kind of the reason why I guess I don't worry about it as much is because the architecture of the program, it doesn't use that. You're going to hit the CPU bottleneck of a computer with 16 gigs of memory far quicker than you're going to hit the 16 gigs of memory itself. Because, for example, a 10,000 particle simulation on this computer is only using maybe 30 megs of RAM at a time. And that's 10,000 particles. You can scale that up quite far before you hit, serious memory limits. And I've used a bunch of different tools like Valgrind to minimize the memory leaks that this program contains. In fact, running a leak check, the most that is ever leaked is not even my fault, it's OpenMP's fault, because there are certain inherent memory leaks inside of OpenMP that are unresolved when the simulation ends. So through minimizing memory leaks, it kind of kicks the can of memory being an issue so far down the road that the CPU becomes a more immediate problem, if that makes sense.
So you mentioned looking at periodic boundary conditions. Is that something that is specifically limited to the Barnes HUD implementation as far as working well, or?
I don't think it's inherently limited to Barnes HUD because it's, as long as you're keeping track of everything that's going on in the main simulation bounding area, it's pretty easy to just do a coordinate transformation to compute the forces that you need to compute. And there are different ways of implementing periodic boundary conditions that I've looked at. I haven't, picked which one that I want to go down the route of. At the end of the day, it's kind of my hope, long-term hope, because I've been working on this for so long, to get it in a state where periodic boundary conditions are present. That's like the #1 roadmap goal right now, because this thing is really capable. It can, run these incredibly monstrous simulations. The main problem, though, is from a cosmological perspective, they're not very useful because we don't have those periodic boundary conditions. So Barnes HUD right now is currently not that much of a limiting factor. When it comes to implementing other different kinds of force computation, like particle mesh and things like that, that's adding in more different ways of dividing the simulation space. That's where it kind of gets messy, because once you start adding in more ways of dividing up the simulation space, you need to be more careful with how these systems are interacting with each other. But as of right now, the architecture is good for if I was to just go down the Barnes HUD only route and implementing these periodic boundary conditions.
So the plots are useful to compare, but do you have any visualizations of, say, what n squared versus the n log n using the plot tree that we can see side by side? Or any kind of animations running?
I mean, I can give you an animation real quick. I can give you a simulation. So like the parameter file system here, I can just make it run for 10,000 time steps. It's going to take my computer a bit to compute that, but go into.
And I saw a screenshot, while you're doing screenshots of the code in the report, but is there a GitHub or other place?
The GitHub, I'm planning on putting up today, because the main reason why I hadn't uploaded it yet was because from a documentation standpoint, there was none. And so explaining how these systems work together, the code has been fully commented. So it's in a ready state to be put up there. The old version of the code is there. However,
That's the Sings one.
yeah, that's the Sings one code, but it is, try to scare your eyes from it. It's pretty awful. All right, so making it run 8 threads, my computer is going to be unhappy with me, but while it does that, the main, I did show a GIF briefly earlier that was really short. If I could get the internet, I have a longer GIF.
Loop the short one.
Like if I do have a much longer one because it's going to take a while for this to compute in, even with 8 threads, just because I'm not pushing. But I could do that. Making it run 10,000 time steps. Yeah, if I go to the actual project itself, you'll see it's presently constructing, filling this folder with individual simulation frames, and then I'll just use FFmpeg to make a thing. All right, it's finished. So going into frames and running FFmpeg. Yep, overwrite.
While you're waiting on that one to plug and chug, can you talk a little bit about the snapshot data format? Is that just a giant CSV file of parameters?
It basically is. The source code for writing snapshots is really dumb because this is basically it. It just throws in, it writes the number of particles, it writes the simulation configuration, and then it just writes the particle list. It's almost like a bitmap, but for particles.
Okay. And error handling on that one is it succeeds or fails?
Yeah, and it'll let you know on that. So this is it running 10,000 simulation time steps on just a random distribution. This is an area where I would really love to have periodic boundary conditions. And this is using the Barnes-Head approximation. And that's from just now. If I was to configure something else, that would take a while. Just because I had this starting condition already pre-compiled.
And this is playback, so this would run how long? How long would this take?
Couple billion years.
I mean, in the code running.
The code running. So this I just did. It shows the.
Well, that was just now.
That was a 2-minute run.
Oh, okay.
Running FFmpeg on it.
That was
Took half as long.
on 8 threads. That was 47 seconds.
Okay.
And that I believe was with 10,000 something particles, or 10,000 time steps, and then like 2,000. I don't know the exact counts off the top.
Have you validated the time run scaling on if you just add a 0 or double the number of particles on a simulation?
Yes. So that's actually like a really great question. When it comes to particles themselves, they don't influence the simulation thing itself. Inside the simulation configuration itself, there is certain information that keeps track of the length scaling and things like that. Units are like that. There are multiple internal representations of the units, and basically it does a high order, scientific notation approximation where it just roughly keeps the things within the relative magnitudes of each other. So if this is a simulation that you're running over millions of billions of years, having the gravitational constant be 10 to the minus 11 is not going to be particularly handy. And you're also going to run into floating point errors. But certain things like length scales and stuff like that, there is an internal representation for that, and it converts. It's not exactly accurate, but to within a order of magnitude.
You mentioned in next steps using a fast Fourier transform to compute the gravitational potential
Yes.
in the cells. Can you, at a high level, describe how what's coming out of the Fourier space?
Yeah. So what's coming out of that is I think it's called like the cloud and cell particle mesh method. You're basically partitioning the space into equally sized cells in 3D, they're cubic cells. Oh, just one thing I'd like to note, even though this is 2D, 3-dimensional depth is kind of represented by dimness. So further things in the z-axis are still represented there. The fast Fourier transform allows you, it's through Poisson's equation, but what you're getting is very quickly, whichever FFT you're using, like the 2P algorithm, for example, which is what I tried to implement and kind of failed at implementing. What you're getting is very quickly computing the gravitational potential across the entire simulation space, and then you apply it to a particle. You do run into accuracy problems for particles that are within these cells because these cells are arbitrarily sized, and adding more and more cells is not entirely space efficient. But there are workarounds around that like default to the direct method. But it's at a very high level, you're using a bunch of equations that I don't remember their names of to get the potential for this entire space.
So you're getting like a frequency distribution.
Yes.
So what might the frequencies represent?
The frequencies I would imagine would just be the gravitational potential at any given point. Like the magnitude of the frequency that is, if that explains it. This is definitely a future goal, and I think a point that I do want to highlight on is with this project, especially coming out of it and looking towards the future, a lot of the limitations of things currently were not a fault of programmatic understanding, but rather a lack of my own mathematical understanding. And so with the FFTs, I tried to implement my own FFT that used particle mesh, but I was getting inaccurate results and I couldn't precisely pin down these sorts of things. But that FFT algorithm, because the FFT that you're using is O of n log n, will also be O of n log n, but I think compared to Barnes-Hut slightly edges it out. And
Yeah. My question wasn't to test you, is like, I don't understand it. So I'm
oh yeah, I
trying
know.
to- That's a very good thing.